Right. We're going to go ahead and get started. Welcome everybody to World Quantum Day. Happy World Quantum Day. Welcome to the QIS at the Office of Science's User Facilities and Infrastructure Capabilities webinar. We're really happy to have you here with us this morning or this afternoon. I'm Allison Eckhart. I'm the Acting Director of Communications for the Office of Science. And before we get started, I have a couple of just housekeeping items to go over. This is being recorded, and we will be posting this recording to the Office of Science website once it's processed, probably next week. There are closed captions available for you at the bottom of your screen. There should be a CC button. You should be able to press that and see the closed captions. And we will be taking questions at the end of the webinar, and we'll be using the Q&A function in Zoom. So at the bottom of your screen, there's a Q&A button. You can enter your questions there, and we will answer them during the Q&A session at the end of the presentations. And so with that, I am going to ask Adrian to go ahead and play a video from the Director of the Office of Science, Dr. Azmaret Asfaw-Berhe.
Hello, everyone. It's a great pleasure to be with you on World Quantum Day. Today's panel will engage and share with you all what we're doing at the Department of Energy's Office of Science to advance quantum research throughout our supported R&D ecosystem. I'd like to extend a warm welcome to each of you. I'm so glad to be kicking off this webinar. For those who don't know me, I'm Azmaret Asfaw-Berhe, Director of the Office of Science at the U.S. Department of Energy. Before coming to DOE, I spent about 14 years as a professor at UC Merced as a soil biogeochemist and associate dean for graduate education, among other roles. I've now spent about 10 months on the job, and this first 10 months have been a whirlwind. Depending on the day, I get to be a scientist, a researcher, an advocate for science, a champion for diversity, and on some wonderful days, I get to kick off webinars on cool topics like we're doing today. The Office of Science is often referred, of course, that we often refer to as SC, supports the entire quantum information sciences research community through our research programs, facilities, and user support. So just to give you a bit of an idea, we fund research to the tune of about $8 billion at more than 300 institutions in the country. We manage 10 of the 17 Department of Energy's national labs, really the nation's crown jewels that these national labs are. We manage and maintain 28 scientific user facilities that support more than 38,000 users annually. And those users come from across STEM, including academic institutions, national labs, and the private sector researchers. We also invest in the development of infrastructure critical for QIS. That's what I'm talking about, is quantum testbeds that are available for the quantum community to do your research. Today's panelists will highlight the impact that these capabilities have enabled in their research. Simply put, the user facilities that we manage and the quantum test beds are outstanding. They're built to be the bridge between fundamental science research and all that you do with it in quantum. So I encourage you all to check it out. You will hear about one-of-a-kind instrument for robotic synthesis of 2D materials that's available to the user community. You'll hear from a pioneer in precision instrumentation for detecting quantum phenomenon at our X-ray user facilities. An industry partner will discuss working with DOE-funded quantum computing testbeds to develop and deploy an optimized software stack for business applications. And also amazing, Oak Ridge National Laboratory and the Exascale Computing Project's CANDLE team, where CANDLE stands for Cancer Distributed Learning Environment. We'll talk about leveraging the quantum computing user program at ORNL to advance national language processing for cancer surveillance. Today's webinar will zero in on the computational capabilities and test beds supported by the Advanced Scientific Computing Research Office, as well as the X-ray, neutron, and nanoscale science research facilities supported by the Basic Energy Science program at the Office of Science. All offer specific capabilities in QIS. The world's most powerful supercomputers are now being used to model new materials for quantum devices and perform simulations to predict the power of future quantum computers. New characterization tools and fabrication capabilities inspired by applications in quantum information systems are being explored and made broadly available at our nanoscience research centers, neutron scattering facilities, and X-ray light sources. 2 quantum computing testbeds are offering fully transparent white box systems that allow the research community to explore promising next generation quantum processors that are not yet ready for industry uptake. I would like to take a moment now to share with you the importance and high priority we place on fundamental science and the role that is played by the resources we steward. The Biden-Harris administration, Congress, and the American people have consistently recognized and funded basic science research, much of it done at our national laboratories and user facilities. Together, we're laying the foundations for new energy technologies. We're advancing our goals in energy, environment, and national security. Right now, we find ourselves on the precipice of kickstarting quantum to the mainstream, thanks to decades of investment in fundamental science, the core of what we do really at the DOE Office of Science. DOE-funded researchers have pushed the boundaries of our ability to understand and manipulate quantum states, have peered into the heart of atoms and delivered the know-how and the technologies that folks are now starting to put into real-world use cases. Quantum is just one reason I'm honored to lead the Office of Science, stewarding the investment of more than $8 billion a year in amazing research and incredible facilities that are together advancing the frontiers of science across many disciplines. The quantum information science and technology sectors are full of gee whiz technologies and applications that will truly change our world. And as you all know, it's a massive future job sector. So that's why I want to talk to you about diversity. It's going to take a large, diverse, and highly skilled workforce to power the quantum industries of the future. Those who invest in that workforce and do so in a way that follows the principles of belonging, access, justice, equity, diversity, and inclusion stand to take quantum to the next level. That's why we're working with our national QIS research centers to engage the future workforce in an equitable and inclusive manner. We're investing $15 million with initial funding last year in projects to build and diversify the quantum workforce in our new RENEW program, where RENEW stands for Reaching a New Energy Sciences Workforce. And we're launching $35 million effort to build research capability, infrastructure, and expertise at institutions that have been historically underrepresented in science as part of DOE's FAIR initiative, where FAIR stands for Funding for Accelerated Inclusive Research. I believe it's the responsibility of everyone to ensure that the science we do truly serves the public, all of the public. I'm passionate about building an inclusive communities and providing opportunities for everyone to be able to see themselves in STEM. We're pushing boundaries of human knowledge and building this future together. I hope you'll all have a wonderful session today. I'd like to give a shout out to the BES and Oscar team and the webinar organizers for putting all of this together. And I hope you've all enjoyed Quantum Mania, but I anticipate today's panel might even be more interesting than that. I'm betting on it. Thank you all.
All right, thank you, Dr. Berhe. Now we're going to turn it over to Pranav Gokhale with Inflection. Pranav?
Hey, thanks so much for having me on. I don't know if I'll top Quantum Mania. That's a high bar, is a great movie. But anyways, happy World Quantum Day. It is pretty amazing to see quantum go mainstream. It kind of reminds me of when my favorite alt-rock band went from the radio station no one listens to the radio station everyone listens to. So it's exciting time. So my background, my name is Pranav Gokhale, and I started a software company, a quantum software company, called SuperTech, spun out of University of Chicago with my PhD advisor, Fred Chang. And we were acquired by Colt Quanta last year, which is now named Inflection. And so since last year, we've been happy members of the Inflection family. And what I mostly wanted to touch on here was the amazing opportunities that we've had through the DOE quantum testbeds at Sandia and Berkeley National Labs. But before that, I also thought I'd give a shout out to the DOE for really enabling our startup to exist in the first place. And I was not asked to say this, so this is authentic, but also with budding entrepreneurs who are in the program, I want to point out two programs. So the first is that we got off the ground through Argonne National Labs Chain Reaction Innovations program, where we actually embedded in the Argonne system, built our technology there, interacted with DOE researchers, and that was really pivotal for us to get off the ground. And then the other one is we're really grateful to have the support of DOE SBIR Phase 1 and Phase 2 small business grants. And those have been valuable not only for kickstarting our growth, but also for helping us focus on commercialization and getting a product to market, which is, of course, just as valuable as the actual science and technology. But what I mostly want to focus on with the theme of this panel is our interactions and experiences with two quantum testbeds. So the first is the Berkeley Advanced Quantum Testbed, led by Dr. Irfan Siddiqui. It's one of the most amazing quantum systems on the planet. It's a superconducting system that has set a lot of records for fidelities, low error rates, as well as having one of the most advanced control systems out there, QBIC. And what has been really special for us about the Advanced Quantum Testbed is there's a lot of technical problems and challenges and opportunities in quantum that you only really get to understand when you work with the physicists and the engineers who are on the ground, literally building the hardware and tightening the screws. So one example of that I'll preview for a paper that we're putting out with AQT later this year is QTrits. So many of the folks in this call have probably heard of qubits, which is where you have either the 0 state or the 1 state. But actually on these systems, you can access the 2 states, so 3 states in total as well. And with the experts at Berkeley lab, like Akil and Ravi and Noah, we've been able to experimentally achieve very good control of that qtrit space. And the bottom line here is it's enabled us to explore a technology that is just otherwise not possible unless you're really interacting with physicists. So a very low level interface to their gates. One of the cool things in quantum systems is that you don't just have on-off gates, like it's not just an AND gate and an XOR gate and that's it. You can do fractions of gates. And so we've been doing fractions of 2-qubit gates, which is something that capability that we were only able to get to by working very closely with Susan Clark and Chris Yale at QScout. So the big picture story here is that there's these amazing facilities at the DOE quantum testbeds that have been really impactful for our business. It's actually been a two-way street. We've learned a lot by doing research and development from them. And it turns out that our software has been useful to them too. Both labs, as well as Argonne National Lab, have licensed our software. And I think it's a really good example of interaction between the DOE and national labs and industry and commercialization. So that's my little statement about the interactions that we've had with the testbeds. And I definitely encourage other folks in this call to consider taking advantage of the opportunities at the testbeds. I also want to highlight that they've done a wonderful job with workforce development and broadening participation, which are very critical, as the previous speaker mentioned. So yeah, thanks for your time. And I want to give a shout out again to the testbeds.
Thank you, Prabhnav. Now we're going to turn to Dr. Kathleen Hamilton from Oak Ridge National Laboratory.
Hi, thank you very, very much for allowing me to participate in this event. I'm very happy to share some of the research that's going on at Oak Ridge, and specifically, I'd like to highlight some of the exciting resources and computing resources that we've used. So I myself am an early career researcher at Oak Ridge, and I work in quantum machine learning. My research really is focused on developing scalable algorithms that can one day solve very challenging problems in areas such as high energy physics, healthcare, and other areas of scientific computing. And what I'd like to focus on in my talk here, this presentation, is the computing resources available at Oak Ridge. And there's two in particular I'd like to focus on: the high performance computing resources through the OLCF, and also Oak Ridge's quantum computing user program called QCUP. QCUP was established in 2017 to enable access to industry-leading resources for quantum computing. And the capabilities of these platforms are helping us to advance scientific discovery and innovation. And since it was established, QCUP has worked alongside the Oak Ridge Leadership Computing Facilities, the OLCF, and their high-performance computing systems to enable hybrid computing applications, and with the goal of advancing scientific discovery. And the project I work on specifically is the exascale computing project, the CANDLE project. And we think this is a really prime candidate for this these hybrid workflows and this integration of both quantum processors and OLCF resources. So just a quick note about the CANDLE project. This is a strategic partnership between the DOE and the National Cancer Institute that is focused on developing AI solutions for cancer research. With the OLCF resources, we can implement very large-scale distributed workflows with classical data. And inside those workflows, we can call QCUP resources to execute components of our workflow on quantum processors and take the output of those circuits and then further process that and use that in our distributed workflows. By providing access to state-of-the-art quantum platforms, the QCUP gives us the opportunity to really see how far we can scale up our applications, really push the envelope, and take advantage of the advances in today's quantum technology. But in addition to the access to platforms, the QCUP is also a valuable asset to connect domain scientists with researchers in quantum computing. And the QCUP itself holds an annual user forum. During that time, the community can come together and really highlight exciting progress and share research, particularly in applying quantum computing to new and exciting scientific problems. And this is very beneficial to existing DOE testbeds, to quantum computing researchers, and to future domain scientists that are interested in quantum computing. And I'd just like to emphasize that this user forum is just absolutely valuable for both sharing research, sharing progress, and finding new areas of collaboration. So beyond just the scientific opportunities, the main thing to highlight, or another thing to highlight, is the exciting byproduct in how this is allowing us to foster workplace capabilities at the intersection of large-scale, high-performance computing and quantum computing, and also really fostering collaborations between quantum computing scientists and domain scientists. So that is, I believe that is all I'd like to touch on. Again, just thank you for letting me participate in this event today.
Thank you, Kathleen. All right, next we will go to Dr. Suji Park, who is with the Brookhaven National Laboratory, and we'll give a minute to get her presentation up. All right.
Hi, I'm Suji Park. I'm very excited to be a part of this amazing webinar and to introduce our new facility, QPress, Quantum Material Press, developed in Brookhaven National Lab. Let me start with a brief introduction of atomically thin and two-dimensional materials. Can you show my screen? The slides, okay. Next, in 2010, the Nobel Prize was awarded to two scientists who had isolated monolayer carbon sheet from bulk graphite by a piece of Scotch tape. They found unique properties of 2D graphene, which are different from their bulk properties. And the tape exfoliation method opened a whole new chapter in 2D material research. Next. Okay. In 2018, scientists in MIT found so-called magic angle. Next. By stacking 2 layers of graphene with twisted angle, they could tune a band structure and made a superconductor, which is a very important component in quantum computer system. Since then, a new research field called twistronics has begun. And now we can even tune the material properties by stacking them with a twisted angle. Next. So graphene is the most widely known 2D material, but it is not the only one. There are a broad range of 2D materials with various electric, magnetic, and optical properties. And it has endless potential because we can create a new structure by simply stacking them with different components in different order at different twist angles. Next. In this figure shows their applications for information science. You can see it covers from transistors to various types of quantum bits or qubits. Next. However, these fancy future devices are still produced by human hand, like a handcrafted carpets or something. This process is highly labor intensive with low yield and low reproducibility. Students and postdocs spend days, weeks, and even months on this fabrication process. So here we are, we try to overcome this situation. CFN, mainly I, designed and built a robotic 2D fabrication system funded by DOE. Next. So let's see the movie in virtual tour. QPress has argon glue box and vacuum environment to protect the materials from air exposure. And we built 3 custom-built robots to exfoliate and find the flakes and make a heterostructure. So this is a roller assembly for exfoliation, and we developed an optimized recipe for maximize the yield of different materials. And we transfer the substrate under the cataloger. We have a machine vision code and optical measurement tools to characterize the flake. And we will share this information with users, and users can pick their flakes and then stack them into a structure using the 6-axis motorized stacker. So we can do this twistronics and other fabrication of new quantum materials. Next. So QPress is still under development, but we are working with users since last year. We have tested and proved that QPress can produce high quality 2D materials with higher yield than manual process. We believe QPress can help to accelerate the discovery of new generation quantum materials for sure. So bring your ideas and let's work together. Thank you.
All right. Thank you, Suji. All right, and now we are going to go to our next presenter, Dr. Zhi-Xun Shen. Dr. Shen.
Thank you, Alison. Hello, everyone. My name is Zhi-Xun Shen. My research interest is, next slide, please. My research interest is in the scientific foundation for the next generation of quantum material. As illustrated by the Nobel Prizes to the left, the first generation of quantum theory played a vital role in the development of first generation quantum technologies like semiconductors. It changed the way we live. However, adequate quantum theory is yet to be developed for other classes of quantum materials, for example, QPress high-temperature superconductors, as illustrated by the surprising discovery of these materials in 1986 and the Nobel Prize in 1987. Precision measurement of key quantum parameters is imperative to the development of next generation quantum theory in the search for the next magic materials. DOE facilities enable precision measurements not possible any other way. I am both a user and a developer of these techniques. Next slide, please. The technique I will focus on is called angle-resolved photoemission spectroscopy, based on Einstein's idea of photoelectric effect, for which he won the Nobel Prize. In this case, synchrotron-based photoemission records energy and momentum of electrons, as shown in this cartoon here, where photons coming from synchrotron hit the surface of materials and eject the electrons. And you measure the energy and momentum of the electrons. The middle picture is that of SSIL, where much of our experiment was done. To the right, I showed the number of citations of photoemission papers as a function of time. As you can see that there's a very rapid growth of that. As this technique has been applied to many materials, among them is the QPress high-temperature superconductor. That in this case, the foundational discovery was that those materials were found to pair in a very unconventional way. In a superconductor, two electrons form a pair. How they pair tells you a lot about its mechanism. We find that unlike its conventional counterpart, where the electrons pair symmetrically, in the QPress, they pair asymmetrically in so-called D-wave channel. This was unexpected. So this success demonstrates that photoemission can be a quantitative tool to address key questions in materials where reliable quantum theory has yet to be developed. And this success also sets the rapid growth for photoemission as a technique and being applied to many materials. Among them is the discovery of the topological insulators. Those materials have novel properties that could potentially be very important for quantum information processing. Next slide, please. Taking this to the next level, we would like to ask the question, how do electrons and atoms behave in their natural length and time scale? These are hard experiments because the atoms and the electrons are tiny, and as you can see, the length scale is 10 to the minus 12 and 13 meters. That's what you need. They move very fast. You need a time sensitivity of 10 to the minus 13 to 15 seconds. So those are technically very hard experiments. We use ultra bright and ultra fast X-ray laser for recording movies of electrons and atoms in motion. The left is a picture of the linear coherent light source at SLAC, where we did much of the experiment. The cartoon is an illustration of how atoms and electrons moving together. And the lower part is the raw data of electrons and atoms in motion. To give a sense, the whole horizontal scale of this is a picosecond. That is 0.00, the 12 zeros of a second. So you need that kind of precision for this sort of experiment. In this case, we can measure both atoms and electrons simultaneously. I myself didn't think this was possible not that long ago, but now this is a reality made possible by the DOE facilities. What we find is that harmonious cooperation of electrons and atoms enhances properties in a little understood superconductor, iron selenium. Inspired by this success, we are forming an international collaboration led by SLAC and DAISY to have a dedicated instrument. Next slide, please. The future is really bright. We want to engage in synergetic activities using advanced instrumentation, synthesis, control, and simulation. The goal is towards a complete experiment to advance quantum materials by measuring their energy, momentum, spin, time, and space. And all this is becoming possible. I show a few pictures of those instrumentations. I'll be happy to discuss more about them. Thank you very much.
Thank you. Thank you to all of our presenters. We are going to go into our panel now for Q&A. So we'll have our presenters come back and wait for them to rejoin. So we have a couple questions in the Q&A box. If you do have a question for our panelists, feel free to drop it in the Q&A and we will go from there. So our first question, there are significant governance implications and needs with the emergence of more accessible, commercialized quantum systems, data and policy governance in particular. Is there any focus on this aspect yet?
So there's a lot of dimensions to that question, and I wouldn't be able to give a complete answer, but at the least I could say that one of the nice things about our interactions with testbeds has been the contract that you sign with them is all about open sharing of data. And this is data that has scientific value. The idea is when we run experiments on the Berkeley testbed or the QScout testbed, we get to do what we want with that data. And for us, that's to publish it to make it more accessible to the scientific community. Ditto for when we work with the QCUP user facility at Oak Ridge that Kathleen talked about. So I think we're at a stage where we want to be sharing the results of the experiments that we run. And that's the main data and policy governance that's been core to what we do.
Thank you. Any other thoughts on that?
So we are encouraging, companies and other like private sector to use our user facilities as well. But in that case, the research, the data should be, this kind of secret for the company. So I don't know the exact policy of that part, but we do work with companies as well.
Yeah, with proprietary information.
What we do is very fundamental. So all data in theory, anything is published, we will put the raw data to be available for anyone else to analyze or check on.
Great. Right. The second question, could the presenters discuss a little more about how AI machine learning systems may interface with quantum and where we could find further research in this area?
So I'm happy to give an answer to this. And there are a lot of different ways that AI and machine learning can plug in, they can interface with quantum. It can either be through the development of algorithms that leverage both classical and quantum machine learning models. It could be through using classical machine learning methods for better qubit control. It could be in using AI and machine learning models for designing better experiments. So there are a lot of different ways for these two fields to intersect, complement each other, and even grow into new areas of research. It's very exciting.
I can add a note about another direction of that, which is how quantum can potentially accelerate AI machine learning applications. Certainly, I want to also acknowledge what Kathleen said, that there's really cool techniques for using machine learning for quantum. Now, in the flip direction, we've done some interesting work with the Berkeley testbed. It's published now. It's a paper called Swap Networks with Equivalent Circuit Averaging for QAOA. And that was inspired by a machine learning algorithm for clustering, which is a very fundamental unsupervised learning problem. And so there's interesting work being done on how quantum can be an accelerant to machine learning and AI as well.
One way to think about what we do in condensed matter physics really is the materials are doing quantum computing in themselves. And we're trying to figure out a description of that. And any analysis of the data, which can provide guidance to some sort of description, necessarily a lot of that involves classical computing. That in this case, AI machine learning certainly can help with the data analysis and extract information. Sometimes it's difficult to see by human. And so in that sense, there's a synergy.
And I want to add to all these answers. And I know there are some people who actually use the machine learning and AI algorithm to find a new material and new structure in terms of 2D materials, because there's a lot of different possibilities, like the sequence and all this configuration matters. So people use machine learning to find out new capabilities of the 2D material.
Great. So building off your answers, can you talk about successful partnerships that you've seen or are part of between researchers and private sector companies, perhaps, and maybe describe in more detail the kind of data and or expertise of lab staff and companies that have been accessed?
So I suppose both of the examples that I mentioned earlier are certainly falling into this category because we are a private company that interacts very closely with the test beds. And just to say a word or two about how we interact with the test beds at Sandia and at Berkeley. Generally, the way we do it is pair programming sessions. So we get on Zoom, much like this, with the scientists and engineers on the other end. And we just track out a full day to work together. And inevitably, we have a plan, but that plan changes through the day. We encounter bugs that go all the way down to the hardware, how the control on a certain qubit wire may be impacted by crosstalk of another qubit. And that's really both, I think, the fun and the challenge and the opportunity of the process. It's very differentiated from our interactions with commercial quantum systems, which, to be clear, have a lot of value. We're certainly building them ourselves, but it opens new frontiers to the kind of science we can do when we're in this room, virtual room with the test beds. I had the good opportunity to actually visit the Advanced Quantum Test Bed in person a few months ago as well. And so I'm hoping to have more in-person visits as well.
Any other comments on successful partnerships? So why are the user facilities and the resources like the test beds important for the research community? What have they allowed you to do that you wouldn't have otherwise been able to do? Or what research have you seen done that wouldn't have been able to be accomplished without these kinds of resources?
Maybe I can say that, certainly in my field, those facilities provide the kind of precision that is impossible to achieve any other way. For example, the FEL, actually FEL is unique capability. Also the synchrotrons, allow you to do the kind of experiment, otherwise it would not be possible. I'll probably, without those facilities, I'm probably doing very different things. And they are extremely enabling of that. As I showed earlier, taking the movies of atoms and electrons in motion, that sort of things almost impossible, mission impossible, that became possible because of those facilities.
So I personally a user of SLAC and APS, which is the user facility of DOE during my PhD and all the way right now. And I really think that these user facilities are a kind of very important infrastructure on pursuing this basic science and also the applications. And in speaking of QPress, this is like over a decade, a lot of people was suffering from something very basic but tedious process. But everyone knew that we need something else, but it was really hard to achieve in like university level or private sector. But this government national labs put a lot of money and effort to develop this infrastructure for this community, which is very important role of this government in national labs.
Any other thoughts? I guess the next question is, how have these resources changed your research? Did they change the direction of what you were doing or how you did things? I mean, obviously they helped you in some capacity.
Yes, absolutely. In my case, it dictates the direction of my research. In many ways, it's an embryonic relationship. We help drive the technique, and the technique enable us to do the kind of sciences. I would call it the science-inspired instrumentation development. It really needs to be sort of positive feedback of both scientific progresses as well as the instrumentation development, and that I sort of show a slide of what happened over the 3 decades is a pushing of both the in a synergetic way.
Yeah. So where do you guys see your fields in 10 years? And what could help you get to the next step? What resources would you like to see in the next 10 years? So those are 2 different questions.
Okay, let me give a crack on this also. In many ways, coming from Silicon Valley, I looked at this problem not like just one thing, one tool. Really is an ecosystem. I mean, when you look at the success of the Valley, really is the infrastructure, the scale, the talent, openness to new ideas, and of course, there's funding and resource in a very similar way. If I would look at, say, how would I advance some of those kind of experiments, those kind of science, what I do, I would really ask for an ecosystem, a balanced ecosystem with complementary tools and driving the things forward. And for example, I would like to see a better synchrotron with better frequency measurements and better FEL with a better time domain measurement and a better surgical pump to manipulate the material for measurements. Then, of course, it's a wonderful material and a theory, a strong theory component to it, so that the problems are embedded in an intellectually rich environment. Those instruments doesn't work by themselves. They need to be put in an ecosystem to make it work. I think that's very, very similar actually to the outside world. In the same way as I'm sure that the quantum field will benefit from success of some of that. I mean, when you really look at silicon development, it was sort of a virtual feedback system that get established, and this field needs the same thing.
Thank you.
I can also, I can also add a comment about the 10-year horizon of quantum computing. There's 2 directions that really excite me. The first is we're starting to get to the cusp of doing quantum error correction and fault tolerance. And I think that the testbeds will play an important role in de-risking some of the primitives like mid-circuit measurement and readout and resets that are still under development by most commercial players. So I see the work that will happen at the testbeds as being a force multiplier for the commercial work that happens downstream. So that's one direction. The other direction is there's a lot of exciting work emerging on what happens when you combine a quantum computer with quantum data acquired from a quantum sensor at the edge. And one vision of this world is that quantum computers will actually be miniaturized, not like they are right now in the cloud, but they'll actually be distributed and at the edge. It'll take time to get there, but this is the 10-year horizon question. So I think the testbeds can play an important role in thinking about the integration between quantum sensors and the quantum data that they create to the compute.
Kathleen? You say something?
Yeah, I also wanted to just echo what Pranav said. Just as the hardware becomes more advanced, our algorithms can adapt and become more advanced. And we really want to make sure that the algorithms we're developing are taking advantage of all the exciting hardware capabilities that are coming online. And through programs like the QCup, which gives us access to a wide diversity of different platforms, it's really exciting for just the different ways of designing and implementing different algorithms. But also to touch upon the comment about talent, what's really exciting about the next 10 years is the interest from students in the area of quantum computing. So the ability to support things like internships and summer schools, that is exciting for me, to have new people interested in working in computer science, having them come in and just working together to develop new applications and solving new and exciting problems.
I think that another important component of this, really, we have to take a long view and have to be patient in terms of investment rather than up and down. You know, there's a lot of excitement on AI these days, but that's been 4 or 5 decades. Okay, you see a lot of fruition of that. However, you think about the current, the pro and cons of the current AI technologies like ChatGPT in this, but it's a long time. And in the same way, I think the quantum will take a long time, and we should be patient in that. In other words, really need to sustain the effort. And if you go up and down, that really will be
Definitely. So talking about students, how can we better support our students that are interested in this field and the development of the workforce that we know we're going to need in the next 10 to 20 years?
I would highlight making the internship opportunities at national labs more, sorry, what's the word? Making them more publicly aware, making folks aware of the internship opportunities at national labs, developing workshops like the Quantum Computing User Forum. That is a great way to share research. It's a great way to provide tutorials and hands-on experience for people interested. And yeah, that's about it I can think of.
I think get them excited early and build up their confidence in this. That's really important for the students. And I think it's all about getting them excited and find this to be exciting area of research, and also with patience build up their self-confidence. Those are the 2 really components. Adds to what Kathleen was saying, that the opportunities for them to have exposure to it. Many people actually didn't know they have the talent. Once you get them a taste of that, then they realize they can actually do very, very well in certain areas. They just didn't know.
Yeah, I want to second that. And if I can share a little personal anecdote, I was a really bad student in science and technology in middle school. Those were the only classes where I ever got C's. And this was like, getting a C was pretty bad. And the turnaround moment for me, I grew up in Maryland, was we had a lot of excellent science outreach from NIST, which is National Institute for Standards and Technology, which is right next door to us. And those scientists came in and really instilled love for science and technology. And in fact, that's how I first heard about quantum. So if not for those outreach opportunities, I don't think I would have ever entered the subjects that I was worst at.
Yeah, like you said, national labs and other facilities has a lot of outreach programs and internship opportunities for the wide range of students, not only like grade student, but also high school student and undergrad student for the internship opportunities. But I think how many students would know that opportunity is existing actually? So I think that will be another part, like kind of advertisement or like just make a barrier lower for them to achieve.
Yeah. And quantum is such a wide ranging subject, right? There's so many opportunities and so many different ways you could engage with quantum and QIS. Okay. Let me look at the questions here. So what kind of industries do you see being impacted by your research in the future? Where are the applications?
I think certainly I can speak for what we do is fundamental research. I would say a lot about fundamental research is about trying to get a sense of unknown unknowns. In that sense, it's very hard to predict particular industry, particular thing. But we all know from our experience that by exploring that, you find things which eventually becomes very useful of that. When you really think about it, I mean, the understanding of the band structure, how this impact the silicon industry of that, and ultimately you can think about what has happened and changed our life is understanding, control, and optimization of one property of one material, namely the conductivity of silicon. So I would say we are confident that what we do will find things which are very useful for the future, but sometimes it's very difficult to be very descriptive. What's about science really is about explored unknowns. That certainly speaks for my field.
Yeah, I'll second that there's certainly unknown unknowns. I'll also add that one of the really exciting opportunities in quantum computing that folks such as myself get excited about is fertilizer production. Doesn't sound like it has anything to do with quantum computing, but right now we make fertilizer with the Bosch-Haber process that people probably learned about in high school chemistry class. And there's been some really exciting work that shows that if we could simulate a molecule called nitrogenase, it's an enzyme, which would take a quantum computer to simulate, then we could do a better job of producing nitrogen-based fertilizer. And that's something that currently takes 2% of the world's entire energy. So obviously, if we could optimize that process with a quantum computer, it would be really impactful for climate, poverty alleviation, agriculture, economics. I mean, that's a lot of industries right there. But as Professor Shen was saying, there's a lot of research and unknown unknowns to get to that moment. We're going to need big quantum computers to solve that problem. But there's certainly applications that we're excited about in the quantum computing community. Kathleen and I actually were part of a workshop looking at applications to energy as well, power grids. We did this with the largest utility in the US, largest public utility, Exelon. So there's a lot to be unearthed.
In my case, the range of this application is broad. So it really depends on the users what they are working on. And we hope that the QPress or this automated facility is just one step closer to the mass production or more commercial applications of this tiny, teeny flake of 2D materials. we hope that we can contribute that more, real world applications.
And I'd also just like to chime in and add, sometimes you don't know who is going to be impacted until a user brings you just like a really interesting problem that you never even thought of. So that is just, again, just another benefit and a wonderful advantage of these test beds and these user facilities, just connecting people outside of the quantum computing community, having them bring the interesting problems, the large problems, the challenging problems, and then just working and seeing how can quantum computing help. And
So that's a great segue to my next question. How do people engage these resources? How do they get to the test beds and to the user facilities? And this may not be something you all can answer. We might have to have our program staff chime in maybe with some typed answers, but maybe Suji, you might be able to answer this, maybe Kathleen.
Yeah, so a lot of user facilities are proposal based. So you can just contact the staff or managers to be able to discuss like their goal, or just write a proposal and submit, and then like the submit proposal will go through the review process. And if the review verified this is worth giving the beam time or the sessions, then we can allocate the time and discuss the further step. So the first step is writing a proposal and search the capabilities of these user facilities in specific the research goals.
Great. Right. We have a few minutes left, so I wanted to leave a couple minutes if you guys have any other comments or points that you really want to make from the panelists before we wrap up. So anything you want to drive home about quantum or these resources?
I would say this is a really exciting time, enormous opportunities. On the other hand, we are also dealing with extremely difficult problems. Okay, we should not, I think in this case, sustained effort and investment is really important.
I'll second that, and also offer that if any folks in the audience are in industry and curious more about how to interact with test beds, happy to answer any questions over email.
I just want to emphasize that this is free, so feel free to discuss.
Yeah, the resource open to the community. All right. With that, I think we are going to end our webinar. Thank you all. Thank you for joining us. Thank you to our panelists. And thank you for all the thoughtful questions. And happy World Quantum Day. Thanks, everyone.
Thank you.
Thanks.